To my presentation. Before we start, a short disclaimer. As it was requested by one of the referees, I will be mostly giving you a overview of the topic and the project we're working on. This is because the result in this publication here specifically is very technical and somewhat intermediate within this project. So I rather motivate the project itself and then tell you at the end what it is all about. And so we start with a very old problem called Polya's permanent problem, which is about the computation of the matrix invariant called the permanent. You have the formula of it here to the right. To the left of it, you see its cousin, the determinant, which is maybe a little bit more well known. These two expressions look at first glance very similar, but at least computationally, they're vastly different. So the left, the determinant, this is a very easily to compute parameter. Just use Gaussian elimination and reduce your matrix. It works perfectly fine. The permanent on the other side is essentially the prototypical sharp p-hard problem, even if the entries of your matrix are just 0 and 1, where sharp p is a complexity class for counting problems. So this is a very hard problem to deal with in general. I said these two expressions are almost the same. The only actual difference between them is this sign factor here in the determinant. And so because the only difference between these is this minus that pops up sometimes in the expression of the determinant, a question you could ask is, if I give you a 0, 1 matrix A, maybe I can turn some of the ones into minus ones and somehow simulate these minuses here, so that the new matrix A star I get by doing this operation, if I compute its determinant, this actually gives me the permanent of the original matrix. That would be cool because it would give us a nice way to get to the permanent of some matrices at least. And this is exactly what Polya's permanent problem is about. So 1913, more than 100 years ago, Polya asked, for which square 0, 1 matrices can we use this strategy? An answer to this very innocent question somehow was found in the 70s. This is the first answer we have. It's by Little. And the way he expresses his answer is by reducing matrices. So he gives us a bunch of reduction rules. The first two are relatively simple. The first is just you can switch any row, any pair of rows, you can switch any pair of columns. And for the second one, you can take a single one entry in your matrix and turn it into a 0, just like this, if this does not render the permanent to become 0. Then the next operation would be take a row and a column that share a 1 as their common entry and remove both of them. If the resulting matrix still has non-zero permanent, you're fine. And finally, there is the operation of merging special rows or columns. This I will illustrate a little bit. So here we have two rows, and they're special in the sense that they share a column where the entries in this column that are non-zero are exactly the entries in these two special rows. So this is what makes them special. So what I'm going to do is I will remove the column together with these two rows and then introduce a new row instead that has a 1 entry anywhere if and only if one of the two rows from before had a 1 entry there. So you can see here I merged these two rows into the all one row here. The same is true for columns. I have two columns here. They're again made special now by a row that only has its non-zero entries in these two columns. I can merge the columns and get this all one matrix. And this is exactly the theorem of Little. He said that a Polya strategy of changing some ones into minus ones is applicable to a 0, 1 matrix if and only if it cannot be reduced to this all one 3 by 3 matrix that we just saw. This is a nice theorem. We will come back later to it. At the moment, this is purely theoretical. We don't yet have an algorithm to check it, but we'll explain this in a moment. The way I understand this is as graph theory, because I'm a graph theorist. And luckily, I can interpret 0, 1 matrices as graphs. So I can leave the realm of algebra and enter the realm of graph theory. So you have a matrix A, interpreted as a bi-adjacency matrix. So every row is a vertex, every column is a vertex, and the row is incident to a column if their shared entry is a 1. The rows are pairwise non-adjacent, the columns are pairwise non-adjacent, so I get a bipartite graph like this graph B here in the process. So just remember, this is the definition of the permanent. We have this sum over these products, and such a product becomes 1 if the entry ai sigma I is 1. So if every column is matched with a row where the two vertices in my bipartite graph are adjacent. This means the permanent of A actually counts the number of perfect matchings in B. So this is how we have a graph theoretic interpretation of what's going on. So let's look at our rules. We have, what we can do is we can again delete a entry, make a 1 into a 0. We can also merge special rows. In this case, this would be, we take these two yellow vertices and this blue vertex, we identify them after we have deleted the edge incident with B4 and A4. This is the 0 we made here. And then we get this new orange vertex here. This is represented by this all one row from before. And then similarly, you can see here we have A4 together with B3 and B5 forming these two special columns here, which again can be merged and finally form the all one matrix 3 by 3 above, which is the bi-adjacency matrix of K33. And now we can say that the graph H is a matching minor of B if it can be obtained from a conformal subgraph of G by contracting vertices of degree 2, which is exactly what's happened here. This is what certifies this special property of our columns and rows. In this instance, we mean that the subgraph is conformal if the deletion of its vertex set leaves a graph with a perfect matching, which matches this property from before that the permanent should always remain non-zero when we do any of our operations. So this means Little's theorem says that we can use Polya's strategy to compute the permanent of a matrix if its corresponding graph does not contain K33 as a matching minor. And then the very natural question could be, maybe this is not just special for K33, maybe this works for all graphs. So what do we know? In the 60s, Castelline already proved that this is true for all planar bipartite graphs. And then the theorem of Little, now it's been turned into an algorithm to compute the permanent by both McEwick and Robertson Seymour Thomas, joint announced at STOC97, so still almost 100 years after Polya's question. So excluding K33 works. And then now our project begins. This was one of our first results, now published this year at JCTB with Yiannopoulou and Kreuzer. We could prove that if you exclude any planar graph as a matching minor, this also results in a polynomial time algorithm for the permanent of the resulting class of matrices. And then Yiannopoulou, Filikos, and myself are able to extend this theorem and say if we exclude a single crossing graph, don't worry about this, it's just a slight extension of planarity, then the same holds true still. So we can go quite further. We now contain all of the classes we have seen so far. In the same paper, we also proved that there is a limit to what we can do. So in particular, if you exclude K55 as a matching minor, then the resulting class of matrices still yields a class where computing the permanent is sharply hard. So there is some sort of limit, but you can see there's a gap in between. And the main question now is how can we fill the gap? For this, let's first look at graph minors, because there is a very similar thing going on. And here we found a full solution. This was published at Fox 2 years ago, Filikos and myself. And we say that if I have a class of minor closed graph class, then if this class does not contain all shallow vortex minors, then there exists a polynomial term algorithm for counting perfect matchings, and otherwise the problem is sharply hard on the class. And what is a shallow vortex minor? It's simply a minor of a graph that's shaped like this. You can see here the first three guys in this list. It's an infinite list. And if H is a minor of some member of this list, it's a shallow vortex minor. To prove this theory, we need three ingredients. First, we need the hardness result, that counting perfect matches is hard on shallow vortex minors. This was proven by Kutikapen and Shia, 2021. Then we need, as the theoretical foundation of everything, the general structure theorem for H minor free graphs, proven by Robinson-Seymour in their monumental graph minor structure series. And then finally, we need a bunch of algorithmic tools to count perfect matchings on the pieces we get from the general graph minor structure theorem, and also to propagate these partial solutions we get through the emerging tree-like structure. So these are the three ingredients. Let's see what we can do. So the first one was the hardness result. And indeed, you can see here, I slightly changed the graphs. These are now the matching version of the shallow vortex grid. And we were able to prove in this Soda paper from last year that on the class of matching minors of these objects, counting perfect matchings, or in equivalently computing the permanents, remains sharp p-hard. So the second thing, what we would need is now we would need a general structure theorem for bipartite graphs excluding some matching minor. This is clearly the hard part because it's a very deep theory in graph minors. And then lastly, what we would need is a toolkit of algorithmic tools to handle our the emerging structure that hopefully comes out of two combined small partial solutions and fully compute the number of perfect matchings in the graphs we are given. So this third point seems to be mostly fine. There are some details that need to be checked, but at the current stage, this is probably not the hard step. The hard step is the second one, namely this general structure theory. So how would you prove such a general structure theory? So the first one is you need a notion of tree width. This is what Robinson-Seymour did. They invented tree width for this reason. And then you need to prove that there is a duality between you either have a graph of small tree width, which is a case where we are fine, we can compute the number of perfect matchings, or you have a large wall or some sort of structural certificate that says the tree width is large. And then as a second step, you need to describe the local structure of your graph with respect to this wall. So you want to understand how does this wall appear within your graph if you exclude a fixed minor or matching minor. Finally, you want to understand how does the entire graph attach to this wall. And then once you know if you're given some wall and how does the graph look like that attaches to the wall, you can start arranging the walls in the graph in a tree-like structure and obtain a global structure theory as the fourth step in this very condensed roadmap here. So the very first step, this duality, tree width or large wall in a matching theoretic setting, has been solved by Michael Hutzel, Roman Rabinovich, and myself in 2019. So we already have the so-called grid theorem. First step is taken care of somehow. And it is this second step, what does the local structure with respect to a wall look like? How does a large wall behave in a graph excluding a matching minor? That's the result of today. This is usually known as the flat wall theorem. And on the next and last slide, I will show you what it looks like in the matching setting. So here we have a statement of the matching theoretic flat wall. It says there are two functions, f and alpha, such that for every bipartite graph with a perfect matching m, if this graph does not contain KTT as a matching minor, but it has a large enough wall whose matching aligns with the matching m, then there exists a subset of edges of m, not too many of them, and a smaller wall within W, which is flat in B after I delete the endpoints of this set A. What does matching flat mean, or what's a wall even? So what a wall is an annulus shape like this, you can see these are many M alternating concentric cycles and they're joined up in a specific way. And then there is this set A of small size. If I delete it, it somehow removes all of the jumps over this wall. This is essentially how you can see it. So it cannot start somewhere in the wall, follow along an alternating path, and then end somewhere else in the wall. This means, and this is what the word matching flat tries to capture, that essentially anything that's attached to the inside of the wall, so anything that sits between this outermost and this innermost cycle here, can be separated from the part that attaches fully to the wall by very small, very specific separators, namely by 4 cycles. So anything else that's inside of the graph hides behind these small cycles. This is in particular anything that would break planarity. So the graph that attaches to the wall itself can be, under certain circumstances, seen as a planar graph. And that's the end of my talk.